All right. Well, I'm happy to be here today. My name is Elizabeth or Zibby Turtle. I'm a planetary scientist at the Johns Hopkins Applied Physics Laboratory here in Maryland. And I work as the principal investigator for the Dragonfly mission, among other projects. And I'm happy to talk about Dragonfly and what we'll be doing at Titan with this mission. I do like to start by talking about the fact that, like any mission, this is the result of um, a large group of people. We have a very large team of people across the country and around the world working on different aspects of Dragonfly. APL is the managing institution, and we have a number of partner centers and different NASA centers across industry and academia as well. So this is a picture from our recent team meeting held at APL in January around that very large snowstorm we all had, and just representing the work that I'll be presenting today, of course, represents the efforts of a very large group of people. Dragonfly is a New Frontiers mission. It was selected in 2019 as the 4th mission. So this is the same mission category as New Horizons that went past Pluto, and Juno that's in orbit at Jupiter, and OSIRIS-REx that brought a sample back from the asteroid Bennu. So Dragonfly is the 4th mission in that program. We, at this point, are into integration and test. We are through a number of the milestones leading up to that. We passed our critical design review just a year ago in April 2025. And we are now into the build of our flight hardware for the vehicle that we will send to Titan. We're scheduled to launch in July of 2028, and that gets us to Titan in December of 2034. So I'll talk a bit about why we want to go to Titan, what we want to do there, what we know about Titan already, and then how Dragonfly is designed to explore this environment and answer some pretty exciting questions. One of the reasons to study places in the solar system is that we don't actually know how life came to form on Earth. And it's really difficult to study the prebiotic history, the history before biology. Here on Earth, the geologic record is overprinted in many places by the biology that is so common on our world, fortunately for us. So we look to other places in the solar system that can provide pieces to the puzzle of these early chemical processes that, at least in the case of Earth, eventually led to biology. And Titan is very like the early Earth chemically. It's different in other respects. I'll talk about the Titan environment, but chemically it is very similar to the kind of chemistry that would have been present here on the early Earth before biology developed. And that's why it holds really important keys to understanding the chemical origins of life. So this is Titan. Titan is the largest moon of Saturn. It stands out here because it's larger than its siblings in the Saturnian system, but also because it has an atmosphere. And at visible wavelengths, it's actually difficult to see through the full atmosphere down to the surface. It's possible, but there's not a high signal to noise. This is actually really unusual. It's unusual for a moon. It's the only moon that has a dense atmosphere, but it's actually not that common for planets either. Titan is slightly smaller than Mars in size, but its atmosphere is denser than our atmosphere. The density atmosphere at Titan is 4 times that here on Earth. The atmospheric pressure is 1.5 times that here on Earth. So it's really quite a unique place. Just some specifics about the environment. The gravity is about 1/7 the gravity here on Earth. We'll come back to one of the reasons that's beneficial for us. It is a cold place. It's out at Saturn's orbit. The surface temperature is 94 Kelvin. So at these temperatures, the bedrock composition is water ice, and the atmospheric composition, like our atmosphere, is mostly nitrogen. And then there's a few percent methane, which does some very interesting things. I talked about the atmospheric parameters. Because of the dense atmosphere, And the long days, Titan's day is 16 Earth days long. It's very long seasons with a 29.5 year. The difference in temperature on Titan from day to night, from summer to winter, is very small. It's about a degree. So although the surface temperature is cold, it's pretty much constant. We don't have to design a thermal system to be able to manage the really large thermal swings that one would have to, survive on Mars or the moon or even here on Earth, as the temperature is ramping up rapidly this week. Titan is quite far from Earth. So the one-way light time is actually 70 to 90 minutes. So that's something that we need to plan for in our operational considerations. Everything needs to be able to be done autonomously. At this distance from the sun, there's a reasonable amount of light still. The illumination is similar to or better than the full moon on Earth. So it's actually a decently bright place to explore, which is great. And then, like many of the moons in the outer solar system, it turns out that Titan likely has an interior liquid water ocean down below a very thick water ice crust. So Enceladus and Europa have thinner crusts, or at Enceladus, the connectivity between the interior ocean and these plumes that are coming through the ice shell and erupting. On Titan, the ice shell is very thick, probably 100 kilometers thick or so. So I mentioned that not nitrogen, well, it participates, but methane does a few different interesting things at Titan. One is that it breaks down at the top of the atmosphere, and the remnants of the molecules recombine to form very complex organic molecules. And this is what forms the haze in Titan's atmosphere, these aerosols in the atmosphere. And they eventually fall out onto the surface of Titan. But because Titan is an icy satellite, the surface is made of water ice, and at times or locations in Titan's past where the icy crust has melted, there's been the opportunity for these very complex carbon-rich molecules to have mixed with liquid water, possibly for extended periods of time. So that's one of the things that makes Titan such an important destination for understanding the chemical processes that might have occurred on the early Earth, because we have a very similar combination of materials, liquid water and complex carbon molecules. Titan's year, as I said, is 29.5 Earth years. The axial tilt is a little more than Earth's, 26.7 degrees. And as I mentioned, the day on Titan is a little longer than 2 Earth weeks. So we have just passed the northern autumnal equinox, and Titan is heading back toward northern winter and southern summer. Dragonfly, I guess I'll actually talk about the timescale a little more as we move ahead. One of the things we've learned is from previous missions is aspects of Titan's weather over its seasons. So this will put a series of slides to kind of put the exploration of Titan into the Titan year. So when Pioneer 11, Voyager 1, Voyager 2 flew by, late 70s, early 80s, it was around the northern vernal equinox in Titan's year. And there's an image in the upper right corner here of what Voyager 2 saw. So this is kind of true color image of Titan. It's kind of what you'd see with the human eye. It wasn't until the 90s with the Hubble Space Telescope that it was possible to really start to image the surface of Titan. So of course it's low resolution, but nonetheless it revealed surface features, and as adaptive optics became more and more capable, there were more opportunities to see the surface of Titan. And so we knew just before Cassini arrived in 2004, we knew there were bright areas and dark areas on the surface, but we didn't know what they were made of. And of course it's low enough resolution that we really couldn't tell what those structures were. But we knew it was surface material, and we knew it was the same. So it wasn't something moving in the atmosphere or on the surface. The Cassini mission was a joint NASA-ESA mission. Cassini is an orbiter that arrived in the Saturnian system in 2004 for a nominal 4-year mission that was extended twice to extend through the northern summer solstice. So it arrived, Cassini arrived in kind of January of Titan's year, late northern winter in Titan's year, and stayed in the system, making observations of the entire system, including over 120 flybys of Titan for 13 years. And over this time, got to see almost half of a Titan year and watch the weather change on Titan. The ESA portion of the Cassini mission is the Huygens probe. This is a probe designed to study Titan's atmosphere. So it was released and descended down through Titan's atmosphere in January 2005. The atmosphere is very extended. So the mission was designed to really study the aspects of the atmosphere through this descent. It's about a 2-hour descent to the surface of Titan. At the time when Huygens was designed, it wasn't known if the surface of Titan could be covered entirely with a liquid ocean of methane. So the Huygens probe was actually designed to be able to land on a solid surface and make measurements of the solid surface, or to be able to land in a liquid and make measurements of a liquid were it to land in a global methane ocean, which is a pretty impressive engineering feat. So I'll talk a little bit more about what we learned from both Cassini and Huygens. But to put the Dragonfly mission into this same year, we actually arrived with Dragonfly with a timescale of the New Frontiers mission opportunity. We arrive in December 2034, which is basically a Titan year after Cassini and the Huygens probe descent. And so that's really valuable in that we know what Titan's atmosphere was like at the same time of Titan's year. It doesn't change dramatically, but nonetheless, we have that kind of atmospheric truth from the experience with the Huygens probe to help the design of Dragonfly. So this is a map of Titan. From the Cassini mission, there were a number of instruments on Cassini designed to be able to observe the surface of Titan. The methane in the atmosphere is one of the reasons it's hard to see down to the surface. There are a few windows in the absorption spectrum of methane, especially in the near infrared. Also, the haze in the atmosphere, the scattering from the haze is quite dramatic, and that gets better at the longer wavelengths as well. So the Cassini imaging system, the imaging science subsystem, the two cameras had filters at 938 nanometers designed to see down just into the infrared, designed to see down to the surface. And then there was a visual and infrared mapping spectrometer that was sensitive out to 5 microns that was able to see down to the surface at a series of wavelengths. We don't have a continuous spectrum of the surface because of the methane in the atmosphere. But nonetheless, with those different atmospheric windows, we're able to see that there are different materials on the surface. And if you remember the image I showed earlier from HST or from Keck, we see the same darker regions around the equator and then this very bright region at one place around the equator. We don't know the detailed compositions of these materials, in part because we couldn't do full spectroscopy at Titan. But we do see that there are different materials on the surface. So this is a enhanced color map with data from the visual and infrared mapping spectrometer. The darker areas here are darker hydrocarbons, and the brighter areas here are brighter hydrocarbons. And then these areas that show up in purple in this color palette have a little bit of water ice. They're not pure water ice, they just have a little bit of water ice. But nonetheless, one can see that that's kind of correlated with a few of these places that are impact craters, which is one might expect. So one of the big questions, of course, had been, what are these dark regions around the equator? Are they potentially seas instead of a global ocean of methane? Are they seas of liquid methane? And it turns out they are seas, but they're not seas of liquid, they're seas of sand. So the other instrument that Cassini had, or another instrument that Cassini had that was designed to study the surface of Titan, was a radar. And it had a synthetic aperture radar mode. And so what you're seeing here is two synthetic aperture radar images of the surface of Titan. The areas that are bright are areas that are rough at the wavelength of the Cassini radar, and the areas that are dark are areas that are smooth at that wavelength. And the wavelength was 2.2 centimeters, or about an inch. So these areas that show up as bright are kind of gravelly, and these areas that are dark are very smooth. And what is wrapping around the equatorial region of Titan here turns out to be sand dunes. We don't actually know how Titan we don't know what the sand, well, we know kind of what it's composed of. We don't know how it's made on Titan, but clearly it is produced in large quantities because those regions are these vast seas of longitudinal sand dunes. And I'll talk a bit more about that toward the end when I talk about where we're going to be exploring with Dragonfly. But what you're seeing here is these longitudinal dunes wrapping around other features on the surface of Titan. And so these dark features on the right are these dark sand dunes wrapping around rougher hills. There are few impact craters on Titan, as I mentioned. Like Earth, there aren't many, and that's because there are a lot of processes eroding and modifying the surface and burying the craters. And so it's got a fairly young retention age, just like here on Earth. But there are a few. This is the Synlap crater. It's the one that's over here. This, again, is a synthetic aperture radar image. You can see the dunes also kind of encroaching on the deposits around this impact crater. This is about 80 kilometers in diameter. The largest crater here is Minerva. The whole structure is about 400 kilometers in diameter. There are tectonic structures. There aren't global tectonic patterns the way we're used to here on Earth, but there are hills or mountains, depending on your perspective. They're typically about a kilometer or so high. So they're not, like most icy satellites, there's not a lot of dramatic topography. But nonetheless, there are tectonic structures, regions of uplift. Again, in all of these places, especially at the low latitudes, we see these dunes, kind of wrapping in and around them. And so the youngest features that we see in a lot of the images are the dunes, kind of superimposed on the icy substrate. There are hints of cryovolcanism. This is cold volcanism, where the lava would be liquid water. And it's one of the things that has been wondered if that is, common in the outer solar system on icy satellites. Clearly at Enceladus at Saturn, there are, jets of water vapor being erupted, and that is one form of cryovolcanism. One of the questions is whether you could have the same kind of cryovolcanism on Titan that we have as in terms of volcanism here on Earth, where you have flows on the surface. And one place that has the potential to have had that kind of activity is near Sotra Patera. This is a deep, almost a mile, a little over a mile deep pit right next to a mountain. That's almost a mile high. Having those two things right next to each other, the easiest way to explain that is kind of a volcano of some sort. And if you look down on this structure, you see what looks like a flow field here, possibly. There was nothing warm seen by the longer wavelength infrared instrument that Cassini carried, the Sears instrument. So there was nothing warm, nothing active on the surface of Titan in the present day. But in the past, possibly, it's possible there could have been cryovolcanism there too. One of the other really interesting things that methane does at Titan is it plays the role that water does here on Earth. So these are two near-infrared images of Titan. This is at that 938 nanometer, where you can see down to the surface. This is These are two images of Titan's kind of North Pole. The North Pole's about here, kind of between the large dark features on one side of the pole and the lots of little dark features on the other side of the pole. It turns out that there is liquid methane on the surface of Titan. It is mostly at the high latitudes. And so there are these large seas. The largest is over 1,000 kilometers long. And that's Kraken Mare, Ligeia Mare. The top of the image on the right is about 500 kilometers across. These are large seas of liquid methane and ethane. And on the other side of the pole, those small features that are dark are it's just a vast sea of lakes of liquid methane. The very bright features on the left, and then in the series of images, the movie on the right, are clouds. And these are methane clouds in the atmosphere. With Cassini, we actually saw evidence of rain on the surface darkening a couple of times during the mission as a result of large outbursts of clouds. And the clouds were seen to follow the subsolar point. So this is an image taken toward the end of these observations are taken toward the end of the mission, where the North Pole was illuminated as we got toward northern summer, and the cloud activity had migrated to the north. When Cassini arrived, all the cloud activity we saw was at the South Pole, near which was eliminated all the time because we were in Titan was in southern summer. Since the end of the Cassini mission in 2017, we have been using ground-based and space-based telescopes to be able to continue to monitor the weather. One of the great new assets, of course, is JWST. And we have some observations. We've had some opportunities to make observations of Titan with JWST, and in some cases have seen clouds. And then we were able to follow up with Keck and use other Earth-based telescopes to track the weather. I mentioned that there's rainfall. There are also channels on the surface of Titan. So this is another set of images, is a mosaic of synthetic aperture radar images looking down on the North Pole here. And you can see again these very dark features that are the lakes and seas. The one with the arrow here is Ligeia Mare. That's that one that's 500 kilometers across. So these are, again, quite large bodies of liquid methane. There are channels pretty much everywhere we look on the surface of Titan. This is an image taken by the Huygens probe as it descended down through the atmosphere. So Huygens landed in the region just south of the equator and saw this highland that was very clearly incised by channels, erosion due to fluvial processes on the surface. And this is the view that Huygens saw. It landed in a gravelly plain with cobbles, what look like rounded cobbles, possibly made of water ice. It looks like Mars or like Earth. Various kinds of similar places, similar geologies occur on other terrestrial planets. The image on the right, of course, is just, or not just, but is our moon, to give a sense of the scale. So the cobbles are good sized rounded cobbles sitting in this gravel plain. The very bright feature here, there's a lamp that illuminated the surface for the camera, and what you're seeing here is just the brightness in the lower right of that Huygens image is the brightness from from the lamp shining on the surface. So we know that Titan has the key ingredients necessary for life, certainly life as we know it. There's energy in the form of sunlight that drives this very rich, complex photochemistry at the top of Titan's atmosphere. There's the abundant carbon-rich material that results from that photochemistry that falls out onto the surface, where there's been the opportunity to mix with one of two solvents, or both of two solvents. One is water, which has been available at Titan's surface in the past and in the present day deep in the interior liquid water ocean. The other is methane. Methane isn't necessarily as good a solvent for prebiotic processes, for prebiotic chemical processes as water is, but Titan has had a lot of time. And so it's possible that there could be an exotic prebiotic chemical system on Titan as well that involves methane instead of liquid water. So we have the opportunity at Titan to look for answers to really fundamental questions. What makes a world habitable? What are the chemical processes that led to the development of life? And even could life have developed elsewhere in our solar system? Now, at 94 Kelvin, it's not really an environment that is conducive to life as we know it, certainly. And really what we're interested are those prebiotic chemical processes, the chemical steps that were taken before the leap from chemistry to biology. So what we have at Titan is this excellent natural laboratory where these chemistry experiments that we'd like to be able to do in the lab, and we can do in the lab, but we just don't have the same time scale. We can do experiments over years, maybe, whereas Titan has had the opportunity to do these experiments over much longer time frames, thousands of years, maybe substantially longer. And the results of those experiments are sitting on the surface, waiting for us to pick them up. And so that's what Dragonfly is designed to do. We know from Cassini that there are diverse surface materials and environments and an Earth-like variety of geologic processes and landforms. And the scientific challenge became, how do you get a suite of instruments to multiple sites? But here again, Titan does a lot of the work for us. The atmospheric density being 4 times higher than here on Earth means you don't need as large a wing or rotor area to generate the same amount of lift. And the lower gravity means you don't need as much power to generate lift. So it's about 40 times easier to fly on Titan than it is here on Earth. So that's why Dragonfly is designed as a large rotorcraft. I'll talk about the lander itself, but I'll talk through the mission elements and how we get to Titan. So in addition to the lander, we have a crew stage. This is the vehicle that gets us from Earth to Titan. It has all of the components for propulsion, guidance, navigation, control, telecommunication. However, it's powered and controlled by the lander itself. So this is the crew stage on the left, and on the bottom left is the flight model of the crew stage that's being built out at our partner, Lockheed Martin in Colorado. You see also the entry vehicle. So that is what encapsulates the lander itself and protects us as we come down through Titan's atmosphere. And then in the bottom center, you see the flight heat shield that is also being built at Lockheed Martin. So we have, like Huygens, a very long extended entry. We're used to at Mars having a very rapid several minutes of entry from the top of the atmosphere down to the surface. But at Titan, it's a couple-hour process. The entry interface is up at almost 1,300 kilometers, and we spend much of our time on a drogue parachute until we get down to the lower part of the atmosphere. And this animation will show some of that. So this is the cruise stage releasing the entry assembly. And as we go down through the atmosphere, we will release a parachute that we will spend, as I said, most of our time under the drogue parachute as we descend. And so there's about there's almost 2 hours on that drogue parachute. As we get down to a few kilometers altitude, we'll release the heat shield and pose the lander beneath the back shell. This allows us to be free of the back shell to spin up the rotors, and we'll drop off from the back shell to fly to our first landing site on the surface of Titan. And that entire process takes, as I said, about 2 hours with a flight of 10 minutes or so, depending on the where we are in the landing ellipse and the landing site we find. So this is the lander itself. Like the rovers on Mars, it transports the entire payload from place to place. But in addition to being able to do surface measurements, we can also do aerial measurements as we fly from place to place. Unlike the Mars rovers, we do not, sadly, have a fleet of relay satellites in orbit around Titan. So we actually do direct-to-Earth communication from the surface of Titan via the radial line slot array antenna that you see deployed here in the graphic at the top. Like the rovers on Mars, we use the same power source. It's a multi-mission radioisotope thermoelectric generator. This charges a large battery, and we do almost all of our activities off of that battery. The other output from an MMRTG is heat. And often this is referred to as waste heat, but when you're in a 94 Kelvin environment, there's no such thing as waste heat. And we have a very heavily insulated lander, and we keep all of the heat from the RTG in that interior so that the components are all at an appropriate operating temperature. So this is a large vehicle. We're used to thinking of drones as things we can fly around in our backyard, hold in our hands. You see a picture of me on the lower left here holding one of our prototype rotors. So this vehicle is about the same size as Curiosity or Perseverance, or about the same size as a small car. And that gives you another sense of how much physically easier it is to fly on Titan than here on Earth, because this large vehicle, this large octocopter, is able to fly from place to place under its own power. This is an animation. Again, this will show the components it goes in. So at the beginning, you see the cruise stage at the top, the entry vehicle at the bottom, and we'll go in and see the lander. As I said, the lander has a thick layer of foam insulation. This will pull that off, and you can see the interior structure of the lander. So this was developed from our CAD model, and as it gets in further and further, we'll get in to see the boxes in the interior, the large battery toward the back, and then at the very back is the MMRTG. So the focus of our scientific exploration of Titan is prebiotic chemistry. We want to understand the chemical components available, the real detailed composition of those surface materials, and whether these processes are producing biologically relevant compounds like amino acids and proteins and things like that. And we want to put that into the context of the Titan environment. So we want to understand the methane cycle in Titan's atmosphere, clouds, rain, runoff, whether there are deep methane reservoirs in the Titan regolith. We want to understand the organic cycle, the cycle that mixes, modifies, transports organic material across the surface, and the opportunity for those organic materials to have mixed with liquid reservoirs, especially liquid water, but also liquid methane potentially. We have the capability to distinguish between abiotic processes, purely chemical processes, and biological processes. So if somehow the chemistry on Titan did take that leap to biology, we can distinguish and identify some chemical biosignatures. As I said earlier, we don't think that would have happened on Titan. We really fundamentally want to understand the chemical steps before that. And that's the real opportunity we have at Titan. But if Titan surprises us, we have that capability to distinguish between abiotic processes and biological processes. We have a suite of instruments. There's a mass spectrometer. This allows us to measure the detailed composition of samples that are picked up by a drill. We have a rotary percussive drill, and this breaks up the surface material, and then we can just basically vacuum it into the mass spectrometer to make measurements of the composition. We also have a gamma ray and neutron spectrometer. This allows us to measure the bulk elemental composition of the surface underneath the lander. That helps us to determine whether it's different material, whether we want to take a sample and make a measurement with the mass spectrometer as part of our diagnostic sequence, as well as to understand the diversity of the surface materials. We have a suite of 7 science cameras that range from very high resolution imaging of the actual sample site at the grain size, the size of sand grains, to lower resolution panorama images around the lander, as well as aerial imaging as we fly. And then we have a suite of geophysics and meteorology sensors that allow us to measure aspects of the atmosphere, wind speed, direction, atmospheric temperature, pressure, etc., humidity. And we also have geophysical instruments, including a seismometer. So we'll be able to listen for titan quakes in this really new environment to think of from a seismic perspective, where you have a liquid interior ocean underlying a water ice crust. As I said, we need to be able to do our exploration fully autonomously. So in addition to the cameras, which we use, our navigation cameras, in addition to our science cameras, we have navigation cameras that we use for terrain relative navigation. And then we also have a LiDAR, an IMU, to support navigation on the surface and hazard detection. The region that we'll be exploring is here, just north of the equator. So we will land in the sand dunes in this region that is close to a large impact crater. This is another 80-kilometer or so diameter impact crater. And this allows us to measure a variety of materials with very different geologic histories in a close proximity. So the sand dunes themselves have a hydrocarbon composition. We don't, like I said, we don't know how Titan makes hydrocarbon sand, but it clearly does. And these sediments may be sourced very widely across Titan. So by being able to make measurements of the sand composition, we may get information about a much broader area. The interdune areas are materials with a water ice component. And so on Titan, that might be representative of the primordial water ice crust. And then as we get closer to the impact crater itself, we'll have the opportunity to look for materials that represent the results of mixtures of organics with liquid water at the time of the impact crater formation. So the sand dunes on Titan are a very specific kind of sand dune, these longitudinal dunes that are relatively rare. Well, they're not rare on Titan. They're very common on Titan. They're relatively rare here on Earth. So it's not this type of sand dune we're used to thinking of at the beach or something. There is a very good analog for Titan's dunes in the Namib Desert here on Earth. These are dunes that form in parallel to the primary direction of the wind. So the sand propagation is along the dune rather than perpendicular to the dune. And so you're seeing that in the image on the lower left is the Namib Desert. The image at the upper left is Titan's dunes. And what you see in the lower left is the sand, which has a darker red or redder silicate composition, and then the lighter interdune that is also on Earth a silicate composition. But on Titan, these have very different compositions. The other benefit of this location for landing is that these interdunes are wide and flat. And so you can see again at the lower left in the Namib Desert, there's a person here for scale. The interdunes are a few kilometers wide and hundreds of kilometers long. And if you're going to land a vehicle on an icy satellite in the outer solar system, having a wide flat area is really perfect for a landing site. So that's the other reason to go here initially, is to be able to have these great landing zones. This gives you another sense. This is a drone flight over the Namib. It gives you a sense of the type of dune and this spacing that we have with these wide, flat interdunes and then the dunes themselves. The Dragonfly mission is about 3 years, a little over 3 years, is 74 Titan days of science operations. We will do individual flights of several kilometers. depending on where we land in the landing ellipse, how close we land to the crater, that'll drive how far we travel over the course of the mission. We'll probably fly once every Titan day or once every other Titan day. So that's once or twice a month. So even though we can fly, we spend almost all the time, more than 99% of the time, on the surface, making measurements, communicating back and forth to Earth, sending data to Earth, and then we'll fly for 20 minutes once or twice a month. Over this mission, we'll be able to explore a few dozen unique sites on the surface of Titan in different geologic environments. With the possibility of doing aerial scouting, since again, we don't have assets like MRO at Mars, where you have the HiRISE instrument that can do very high resolution imaging of the surface. Fortunately, we'll have the opportunity to be able to scout things ourselves, to take images and come back to a previous landing site, send the images down, and then take a look and see what looks like a good and interesting new landing site. The cross-section at the bottom is very vertically exaggerated. We'll travel from the dunes and inner dunes into deposits associated with the crater. The dunes themselves are 50 meters or so high, and the x-axis in this cross-section is about 200 kilometers. So as I said, the topography on icy satellites is pretty low, and that's certainly true of this region on Titan too. So there's been a lot of work going on. A lot of the work is don't need to really invent new technologies. The technologies exist to do what we want to do at Titan, but we need to demonstrate that those technologies work in the Titan environment. And so APL built two different chambers. There's our smaller chamber, our Titan pressure environment chamber here on the left. That is about 5 feet in diameter, and that can go down to Titan temperature and up to Titan pressure. So we're used to having to do thermal vacuum testing, but for Titan, we actually need a pressure chamber in this case. And so we've been able to do a lot of testing of the instruments and other components to make sure that they will function in the cold of Titan's environment. And then we also have our Titan chamber, which we just call Titan at this point. This is a large chamber designed to be able to fit the entire lander. This also goes down to Titan temperature, but instead of going up in pressure, the pressure is designed to account for the higher gravity here on Earth. And so we tailor the pressure so that we get the same thermal convective environment inside this chamber as Dragonfly will feel on the surface of Titan. So that's about 0.5 bars instead, just to offset the higher terrestrial gravity. So what you see here in the chamber is not the full vehicle. It doesn't have the arms and the rotors, but this is our development test model, and this is a full-scale vehicle in the chamber here. We've also been doing a lot of testing of our mobility subsystem, demonstrating the ability to fly on Titan. We were able to take advantage a few times, fortunately, of the transonic dynamics tunnel at Langley in Virginia. And this was last summer, we were down there with a model. So this is what we call a semi-span. It's half of Dragonfly. The chamber, the tunnel isn't large enough to have the full-scale Dragonfly without having a lot of edge effects of the flow. And since we want to see the aerodynamics and the aeromechanics, we really want to have the air be able to flow around the vehicle. So this is a full-scale vehicle, but just half of the vehicle. And you can see the team here. This is the 14 by 22 wind tunnel down also at Langley. And this is about a half-scale model that was being tested there. This is the same on the lower right. This is the same scale model. This is, in fact, the same model with the back shell, so we can measure the flow of air around the back shell. But this is out at Ames at the National Full-Scale Aerodynamics Complex, which is, as you can see, a vast wind tunnel. And it was hugely valuable to be able to show the wind flow and really understand that environment where we do our transition from descent under the parachute to powered flight. One of the other areas of a lot of development has been our autonomous navigation. This is our integrated test platform, and it too is about half scale. And this has hardware and software similar to the Dragonfly system and can demonstrate the ability to do autonomous navigation. We usually fly that here in Maryland, but of course there are lots of houses and highways and things that make it very easy to navigate. So we were able to take it out to the Imperial Dunes in the desert Southwest, where we could fly over more Titan-like terrain with less features to navigate off of. And still, even there, it outperformed the GPS. But of course, we won't have GPS at Titan. So we need to be able to navigate on our own. There's a lot of work. As I said, we're in flight system, or we're in the flight integration and test of our vehicle. This is our flight harness, the cables that will connect all of the different components being installed. And these are some of the electronics boxes being installed here at APL. So at this point, we have a fully functioning electronic model of the lander to be able to demonstrate the different and test out the different types of activities the lander will be doing. And we're starting to build, in fact, we built most of the flight fuselage as well. So there are a lot of things coming together. Things will be coming together very quickly over the next couple of years. We build the lander at APL. And as I said, the cruise stage and the entry vehicle are being built out at Lockheed Martin. So we will send the full lander out to Colorado for flight system testing to do the testing of the full vehicle together. And then the lander actually comes back to APL for final thermal testing. And then everything else meets up again at Kennedy Space Center for launch in 2028. There's a lot of work being done on the instruments as well. This is our ion trap mass spectrometer. This is the flight model for the DRAMS instrument, the mass spectrometer. The part of the gamma ray neutron spectrometer is on, those actually like to be cold. So typically you need a cryocooler, but at Titan, we live in a cryocooler. So that instrument has components that are out on the skids that are just right out in the Titan environment. So we needed to find a way to do vibration testing, environmental testing at cold temperatures. And so one of our partners, Experior, was able to develop a cold system that can sit on a vibration table to do that testing at cryogenic temperatures, which is really impressive. The seismometer is contributed by JAXA. So this is a picture taken last year, just after it was delivered. That seismometer will be mounted on a cable that allows us to lower it to the surface at a landing site where it can have better connectivity to the surface, but then we can retract it again before we fly to the next site. And then these at the lower left, the lower right, are the flight. These are the engineering models, but showing the different cameras and the data recorder as well. So I will close there. We do have an augmented reality model that gives a sense of the scale of the vehicle. I put the QR code up there. This is actually a model that we use. This kind of tool is something we use to be able to practice different kinds of activities with a lander, so you're not practicing or doing something the first time with the flight hardware. So this is a tool, but it's also a really nice way to be able to visualize the lander itself. So I'll stop here, and if there's time, I'll be happy to take some questions.
We have a question from Sandy Perot. Sandy, would you like to ask it?
Sure. I was just wondering if you're going to be using the LiDAR data not just for navigation, but also for topography mapping.
It will give us topographic information. Yeah. So we need to understand the slope. We want to be able to land on reasonably flat surfaces. So we'll have that topography and slope information from the LiDAR to assess the landing sites. Absolutely.
George, go ahead.
How many organizations are involved in this project? This is huge. It's just enormous.
Yeah, like most missions, it's a really large team. There are dozens of organizations. Almost I think maybe every NASA center is involved. A number of universities, a number of industry partners, including Lockheed Martin, Sikorsky. And then we have international partners as well. JAXA, the Japanese Space Agency, contributing the seismometer. The French Space Agency is contributing the part of the mass spectrometer, the gas chromatograph part of the mass spectrometer. And then DLR, the German Space Agency, is also contributing some of the hardware for monitoring the conditions during atmospheric entry. So yes, it's a big team.
Yeah. What's the total cost? What's the total cost of the mission?
So New Frontiers missions are the $1 billion class mission.
You're in a $1 billion class mission.
And of course they're oops, hello cat. Helper. Yeah, so it's that scale mission.
Has all the disruptions of NASA affected you much?
So we've the biggest effect was COVID. We were selected in 2019, and of course everything shut down the next year. We were early in the mission development, which meant that we could keep working remotely to be able to do the development. But as you know, that the impacts of that were felt. We worked very closely with NASA to be able to keep our work going while there were constraints being, that were imposed. And so our initial launch date did move out as a result of some of the complexity during the COVID era.
Mm-hmm.
But it is holding steady now.
So, but this is really a fascinating mission, and there's once in a generation or more time to be able to get to something like Saturn's moon, that really is important one, Titan, and it'll be very interesting to see this play out. Certainly, Huygens was a great mission, gave us a lot of information, and so this will be very fascinating as it goes on. We appreciate so much you taking the time to talk to us. Normally, we have something you probably need, a coffee mug, but I can't give it to you from Colorado. But I certainly hope that you'll be able to come to see us in one of our outreach activities, or come to a regular meeting, which is normally at George Mason. But we come and go with different requirements to different people and different holidays and et cetera, et cetera. But I'm sure you know that. But anyway, this has really been great, and we really appreciate you taking the time. George, thank you again for a wonderful speaker, and thank you very much, ma'am, for your time.
Oh, it's my pleasure I'm always happy to talk about Titan and Dragonfly.
I got another question.
Sure, of course.
The Titan has an ocean. What is it because of the stress, the gravitational stress of Saturn that causes flexing, or that? What makes it liquid?
It could be a combination of the primordial heating and then enough heat due to tidal forces during the evolution of Titan that has allowed liquid to remain in the interior over time. It's really amazing how many of the moons in the outer solar system turn out to have these present day liquid water oceans. Yeah.
This is a fantastic presentation you gave, and it's very detailed, and you explained everything very, very well. Thank you very much.
Glad to hear it.
And I should mention, ma'am, we actually have more people look at these things on YouTube than they do. And now they've discovered they don't have to come; they can watch them when they want to. But so we frequently have double or triple the number of people that are on to it right now within a week of the presentation. But so much technology and change is happening since COVID and all that. But anyway, thank you again for your time and